Welcome to AP Chemistry. These next three videos will cover concepts prerequisite to the study of first-year college chemistry, which AP Chemistry is. This first video will focus on the notion of force. In order to understand what a force is, we need to understand the distinction between distance and displacement. Distance is the absolute change in a given position. It does not matter where you start from, or whether or not you have undergone a positive or a negative change in reference to your original position on a given axis. All that matters with distance is the difference in quantity between the final and initial values, the absolute change, without any consideration, north or south, east or west, on a given axis. Displacement, however, is not the absolute change in a given position. With displacement, it does matter where you begin and where you end on a given axis. Although this seems like a minor distinction, this will matter incredibly when we begin discussing systems in reference to their surroundings. Velocity is not simply equivalent to speed. Speed is the change in distance divided by change in time. A speedometer measures speed. The state speed limit of 65 miles per hour does not consider your direction on the highway. However, velocity is the change in displacement divided by the change in time. Velocity is therefore completely dependent not only on the amount of change that is occurring, but also the direction by which this change is occurring. If a velocity is constant, an object will be traveling in the same speed and in the same direction. That is, their change in position in a certain direction is constant for every given amount of time. However, if the velocity is not constant, if the velocity is changing, then the object will either be changing its speed or changing its direction or both in a given amount of time. Acceleration, therefore, is the change in velocity divided by the change in time. It is how much a velocity is changing in a given amount of time. If a given velocity is constant, then acceleration will be zero. That is, the object will not be accelerating. If a given velocity is changing, either changing speed or changing direction, then the object will be accelerating at some positive or negative, large or small value. If velocity is changing, acceleration is occurring. You already have a strong intuition of acceleration. If you are speeding up in a car, then you are experiencing acceleration. If you are slowing down, then you are also experiencing acceleration. If you are changing direction in any way in the car, even if you are moving at a constant speed, you are again experiencing acceleration. What is so important about this concept? Well, there is only one phenomenon that accelerates objects in the entire universe. That is the application of a force. In other words, forces alone accelerate stuff. All force interactions in nature can be reduced down to four fundamental forces. The gravitational force is perhaps the force that you are most intuitively aware of, the force governing interactions between objects that have mass. However, in the study of chemistry, all interactions that we will work with are grounded in the electromagnetic force. The strong nuclear force governs how the neutrons and protons in a nucleus are held together, and the weak nuclear force governs how radioactive particles decay. Nevertheless, it is distinctly beneficial to us that you have a good intuition of gravity, because many analogies can actually be made between gravitational interactions and electromagnetic ones. For the remainder of this video, we will clarify Newton's laws of motion that are grounded in the gravitational force so that we can make analogies to the electromagnetic force in the next video. Let us begin with the simulation. Note the use of ice and springs in the given system. This is to represent a system in which there is absolutely no friction present. This is not a normal situation. Now, note, before the figure interacts with the object, the velocity of the book was constant and 0. After the figure interacts with the object, the velocity of the book is also now constant, but also non-zero. Therefore, the object must have undergone acceleration. That is, the figure must have applied a force to the object. Therefore, when a force is applied to an object, the force will accelerate that object. And when a force is removed from an object, the object will no longer undergo acceleration. Again, the takeaway is the same. Forces accelerate stuff. So what can we conclude about objects in rest or objects in motion in the absence of an applied force? We conclude that they will not accelerate, that they will be constant or continue to stay at rest, or they will be constant slash continue to stay in motion in the absence of an applied force. This is what we call Newton's first law of motion. Now note, when a constant force is applied to an object, that object will accelerate at a constant rate. This is keenly illustrated through the simulation in which the figure is applying a constant force against a frictionless spring. An impossible situation, but the effect is important to note. Now, what will change if the same constant force as in the previous example, 5 newtons in this case, is applied, but to a mass that is now greater than the previous object? The change in velocity is much slower, and therefore the acceleration is noticeably also much slower. So, Newton's second law of motion states that the force being applied to an object is a function of the mass of that object times the acceleration that that object will undergo. F is equal to m times a. The only difference between this relationship and the relationship which we will use in chemistry is that we will substitute mass with charge. Therefore, if we are applying a constant force to two charged particles, one with a larger charge and the other with a smaller charge, the smaller charged particle will accelerate more, and the particle with a larger charge will accelerate less. In order to understand the third and final law of motion, Let us return to our frictionless surface. Here, we realize that there is a key problem with our simulation. For if the surface were truly frictionless, the figure would never be able to truly apply a force against the object. For in order to apply a force against an object, the figure must first apply a force down and away from the object against the earth, exactly similar to what you do when walking. And in the absence of any friction, there would be no ability for the figure to quote unquote grab the earth and apply a force against it. Therefore, in order to move forward, we must push backward. We must apply a force in the opposite direction that we would like to move. This is because we are literally being repelled forward. That is, being repelled from the earth in order to move forward. For as we apply a force against the earth applies an equal and oppositely directed force against us. And we, being repelled from the earth, move forward. In order to move the objects, the figure must apply a force against the earth in order for the earth to repel both the figure and the object that is pressed against it forward. Thus, Newton's third law of motion states, for every action, that is, for every force that is applied, there is an equal and opposite reaction. That is, there is an equal in magnitude and opposite in direction force that will also be applied. So, does the Earth move when we apply force against it? Indeed, it does. Only the Earth is so massive that the force that we apply against it accelerates it at an utterly imperceivable amount. However, we, being so much less massive, are accelerated forward quite perceivably. This last relation we will understand most acutely in terms of chemistry when we discuss the interactions that are possible with electric fields, both attractive and repulsive, that surround charged particles. We will see this acutely in our next video. The essential takeaways for this video are as follows. Acceleration occurs whenever a particle speeds up, slows down, or changes direction. Without an applied force, particles do not accelerate. The amount of acceleration a particle will undergo is proportional to the amount of force being applied. For every force applied, there is an equal and opposite reactive force. And forces alone accelerate stuff. Till next time, when we consider the mysteries of the absolute, Crip.